Okay, so here's our example. Again, we have the same problem we just talked about. We have emissivities that we're entering, but now you can see instead of the emissivity being gray, we have discretized it into a couple bands. So E4, surface 4 emissivity, we have now got two bands. We're going to say from 0 to 8 micron, it's going to be 0.8. From 8 up to whatever infinity, I guess, it's going to be 0.2. So that's one. The other surface that we're discretizing here is E1, so it's 0.9 from 0 to 22, and then 22 to infinity, it's 0.5. So first thing to notice, right, we have two surfaces that remain gray. We have two surfaces that are semi-gray. Second thing to notice is the bands don't line up. Right? The bands for these two semi-gray surfaces don't align. We effectively then have to introduce three bands. Right? We have a band from 0 to 8. We have a band from 8 to 22 in that region where they don't line up. And then you have a band from 22 up. So the methodology here, let's just kind of sketch out some steps here. So methodology is going to be, one, let's enter the emissivities. Enter emissivity matrix. Okay, instead of a vector here, we no longer have 4 emissivities, we have 4 surfaces with NB emissivities. We have a matrix of emissivities that we have to enter. Enter the emissivities. So we would do areas and view factors. We've already done that. Areas, view factors. 3, what we want to do is, in order to complete this problem, it's really helpful for us to first have guesses for temperatures for every single surface. So we want to go through, maybe if the temperature is not specified, we're going to provide a guess just so we can solve the system of equations and then introduce other bounding conditions. So 3 is we're going to set temperatures. That's sort of a guess if needed. And then determine the emissive powers. Emissive power. And we'll use the black body function for that. Right? So black body function in the band that we care about. And then the last step is remove temperature guesses. Or actually, if you were doing this outside of ease, what you'd actually do is you guess the temperature, you're going to do a calculation, you're going to see that, okay, let's say I had that adiabatic surface, right? The adiabatic surface, of course, heat flow has to be 0. Your guess temperatures are not going to lead to Q dot equals 0. So what you'd actually do is manually go back, adjust your temperature, recalculate, is it closer to 0, right? It's not, guess again, right? So if you use ease or an iterative solver, then it can enforce that condition for you. But if you're doing it in Excel or whatever by hand, you would actually iteratively do this, that process. Okay, so that's the idea. Let's go through the example. Okay. So again, same setup. Parameters, areas. You'll see immediately, though, there's this difference here. So now instead of E1, 2, 3, and 4, we have emissivity of surface 1 in band 1. Right? This is going to be from 0 to 8. This is going to be 0.9. So let's actually look back at the example real quick and remind ourselves. So epsilon 1, whereas surface 1. We said the first band goes from 0 to 22 micron. So to accommodate this band over here, we have to discretize into 0 to 8 first. So to do that, 0 to 8 is going to be 0.9, 8 to 22 is going to be 0.9. So 0.9, 0.9, and then we get our third band from 22 up, right? That's where that 0.5 comes in. Do the same thing for surface 2. Surface 2 is gray. at 0.5, surface 3 is gray at 0.7. So you enter in for all of these. And then surface 4 was just 0.8 in that first 0 to 8 band, and then otherwise 0.2. Okay, so we've entered this in. We're going to then enter in some bands associated with the problem. So band 0 to 8, 8 to 22, 22 to some infinity, basically. Right? So once you get up above a certain level, a certain wavelength, all the energy is basically accounted for. So in this case, we're using 1,000. You could put in like 9999 or something like that, whatever you want. This has to be a number that's big enough that your answer stops changing. Okay, so that is in here. Let's see how the rest of it changes. Few factors are the same. So now we have a change, right? We have, for every surface, duplicate 1 to 4. We're going to now duplicate the band from 1 to 3. And we have this energy balance for the surface. Here we're calculating the black body emission power for the surface in band W for surface I. Right? You can see what we're doing. So it's taking the lambda low, the lambda high, the temperature that we've assumed, and solving for that. Right? Actually, I've already commented out the guess here. But so we provided a guess. We could then go through and solve this at this point. Let's see, we need this information here. So this information is going to be our energy balance. Again, we modify it for the number of bands. Otherwise, it's exactly the same. But we do end up with like Q dot for a specific band. Right? This is for a specific surface and band. Made that point. So then, okay, we go through, we have everything working. Let's say I didn't specify the temperature and I didn't specify this boundary condition. So we solve this, hopefully it solves. And we can look at the answer. So your answer is getting kind of big, I guess. But it's a pretty straightforward method. Let's look and see what all we have. So I've specified all the surface temperatures. But now what I'm seeing is for a surface I, right? So each of these 4 surfaces, here's the heat transfer in each of the radiation bands. So kind of interesting, I guess. Surface 1 is losing heat in band 1, and it's gaining heat in band 1 and losing heat in band 4. So how many? Actually, I'm going to do this backwards. So these are the different surfaces. So actually, this surface is losing heat all the way across, but it's a different amount, right? So it's a different amount that's all the way across. Same thing for surface 2. It just kind of changes, right? You can get different amounts. In this case, it's the same. So, okay, last step is we go back here, comment out our temperature that we guessed, 125, and then solve it for our enforced condition. Again, this is where, like in Excel, you would need to manually do it. You would also want to update the guesses before you do that, which I didn't, but they already were. Okay, and now we see what's going on here. So yeah, for each of these different cases, this is what's happening. So, yeah, I think that's kind of the example. I don't know if there's that much more to talk about here. Any questions? Nope. Yeah, I mean, so like before, like, I'm not a historian of computation, but like before, there were people that it was actually their job to do stuff. Like, so the engineer would pose the problem, come up with an algorithm, right? And that just is a recipe for things somebody has to do. And then some number cruncher would sit down and crunch the numbers for a day, right? So yeah, I mean, the other thing is you just make simplifying assumptions. So instead of doing this, you say, well, my surfaces are gray. Right? And you are wrong, but hopefully not wrong enough that it matters, that you missed the moon or whatever.